Dear students, today we will discuss the topic fixed bias or base resistor biasing. This is one of the basic technique to keep your operating point stable. So this is a circuit. This is a circuit. You can see here. You have a single DC power supply. That is the first point you want to remember. First point. Single DC power supply. In some circuit, we will be having two power supply, that is plus VCC and minus VCC. So I will explain during the condition. Okay, you remember this circuit we are providing only the single DC power supply, and the RB resistor is connected in series between the supply and the base terminal. The RB resistor is a controlling factor here. Based on the value of RB only, the base current is changing. That means the base emitter voltage is changed, that is in the across this base emitter junction, the base current will change. Accordingly, there will be change in your collector current. So I will repeat again, the RB is a important factor. With the value of RB only, the IB current is produced. So with respect to this, the drop across the base emitter also will change. That is the base emitter voltage. With respect to this only, the IC collector current also change. So this is a simple way how the circuit is working. Suppose, if you see what is the merits, the circuit is simple. But if you see the demerits, the IC, it does not have a real. It will be constant. It does not be constant actually. With the changes in the temperature or supply voltage. So that means how we can understand is the IC will be keep on changing. But if IC is changed, the changes cannot be compensated by this circuit because this IC don't have the control over the input. If I am saying your IC is changed with respect to the changes of temperature or supply voltage. Even it is changing, I need to keep your quotient point stable. But this circuit will fail to do that because the IC don't have the control for the input. That is the first thing why this circuit provides the poor stability. Because it don't have the feedback from the output to the input. So this circuit provides the poor stability compared to the other techniques because the operating point will be keep on changing with respect to the changes of the transistor parameters. So that we will discuss in the problem. See, another thing you want to understand here, this is a circuit 1 and this is circuit 2. In the circuit 1 you can see I have connected along with the capacitor the input. That is this is a real circuit with this input signal. In the second circuit, I have redrawn for DC equivalent circuit. That means I have taken capacitor as a open circuit. How this can be? See, we know that the capacitance formula, reactance formula is nothing but 1 divided by 2 pi Fc. When F is 0, the reactance of the capacitance, that is impedance, will be very, very larger. It can be written as open circuit mathematically. By this consideration only, this capacitor has become open circuit. Right? So this is very important to understand. In the DC analysis, the capacitor will be considered as an open circuit because of the higher impedance. Another thing you can see here, small I, capital C. Here you can see capital I, capital C. That means both are capital. This is small and this is capital. The subscript. That means this is representation for total instantaneous. Total instantaneous means the combination of AC and the DC superimposed. DC is superimposed with the AC. When you see this is only with respect to the DC analysis. Now we are studying the DC analysis, right? That's why this circuit 1 was modified as a DC equivalent circuit and we have removed the capacitor and also we consider the source as a 0. With respect to this only, this circuit was redrawn. Here point to remember is IC don't have the control over the input. If changes occur, it cannot be compensated. So that is a reason why this circuit provides the poor stability. And this capital letter, this subscript and this main letter, both are capital. It determines this for DC values. And this Q represent operating point. So here I am going to find what is the operating point equation and what is the collector current and what is the base current. So collector emitter voltage. All are you can see capital letters and VB on. So generally for silicon 0.7, for germanium 0.2, tentatively, not fixed one. Based on the doping, it will vary. So this is about the circuit. So same points are given here. First point you can see single DC power supply. The base current are established through the resistor RB, and the coupling capacitor is act as an open circuit when frequency is 0. That is isolating the signal source from the DC base current. Okay, the RB is connected in series. The base current is controlled by voltage drop across the base emitter voltage. That's it. So we will go to the derivation. See, now I will make it very simple to understand. First, we will be applying the input bias. Input bias. See, by looking this is the input loop. Okay, this is the input loop. We can apply the KVL directly, but for initially we can have a practice by drawing this loop separately. So this is plus VCC, right? So I will be drawing this loop separately, plus minus. This is plus VCC. Then entering at a plus, leaving at a minus, right? So RB, I am assuming plus minus. This is a passive device, right? So I am assuming the polarity. So plus minus. Then this is a predetermined one, plus minus. So plus minus. So what is the drop across this? VBB. And this is the ground. This is the ground. Now you apply the KVL across this loop. This is the direction. Entering at a minus, leaving at a plus. Always you take a leaving symbol. That is my assumption. So you also can take same. That means it is leaving at the symbol plus. So plus VCC. Entering at a plus, leaving at a minus. So I am taking the minus. Minus IB RB. Entering at a plus, leaving at a minus. So minus VB equal to 0. So algebraic sum of the voltage drop around the closed path is equal to 0. That is a Kirchhoff voltage law says. So now from this I can find what is your IB current. That is IB current is nothing but a VCC minus VBE divided by RB. Similarly, I can find what is RB, just rearrange the terms VCC minus VB by RB. This is for input term. Similarly, we have another relation IC equal to beta times of IB. From here I can find your IC also. So beta is a current gain factor. What is the current gain factor? Output current by input current. What is the output current? IC. What is the input current? IB. So that is the relation says beta, right? So beta equal to IC by IB. From here I can write IC equal to beta times of IB. So that is the formula came. So what is IB? We know VCC minus VB divided by RB. So this is for input side. Now we will go to this output section. This output section, right? It is a output bias. So when you draw the circuit, see generally this I am saying it is plus. How it is? I am saying it is plus because this is something like this. Plus minus. So just for representing simple way, we are saying this is a plus VCC. So that means what you are understanding is plus VCC. This way and this way both are same. Just for simplicity, we are representing it plus VCC. When you apply KVL across this loop, what do you get? plus VCC, then entering at a plus, leaving at a minus. So what will you get? Entering at a plus, leaving at a minus. So RC. What is the current across this? IC. Then this drop plus minus plus VC. Right, now you apply the KVL. What will you get? Entering at a minus, leaving at a plus. So plus VCC. Entering at a plus, leaving at a minus. So minus ICRC. Entering at a plus, leaving at a minus. So minus VCE equal to 0. So this is a master equation to draw the operating point. So I'll explain. So VC equal to ICRC. So VC equal to VCC minus ICRC. This is a main master equation. Okay, so now I will arrange this entire thing. Now we will see how to find the operating point. Otherwise, I will make another white screen. I think it's the issue. So what I will do, I will just so what we have determined is the master equation is VC equal to VCC minus ICRC. Now while explaining how to find the operating point. First, output current, output voltage. Okay, case 1, consider you are going to find what is the maximum VC. That means you want to consider IC is 0. That means if you consider IC is 0, your equation will become VC equal to VCC. So this is a point we used to say VC equal to VCC. Yeah? That's all. Now you got one point. Now case 2. In the case 2, what we want to assume, we want to find what is the IC current. How you will identify the IC when you consider VC is 0. So consider VC is 0. So when you substitute VC is 0 here, so what is the equation? IC equal to VCC by RC. From here you can find what is your point. Now you got both the point, connect. That's all. Now you want to find what is the operating point for this. So this point will be VCQ and this point will be IBQ. So how you can find? We know that VCQ formula is VCC minus ICRC. Similarly, we know that this is ICQ, right? This is ICQ. So how you will find ICQ? So we know that IB equal to VCC minus VB by RB. So once you know IB, IC equal to beta times of IB. So that is your ICQ. Now you will get ICQ point, you know VCQ point. Now plot here. So you plot and connect. That is called Q point. That is a Q point. So this is a simple way to understand the load line. This is called load line, and this is called operating point or Q point for the fixed bias circuit.